How do you find the inverse of an n by n matrix? Well, there's a process, and here's how it goes. So if A is the matrix you are trying to invert, what you do is you adjoin A to the appropriate sized I to form the matrix AI. Okay, so if this is n by n, say if this is 3 by 3, then you'll put the I3 here, and you'll have a 3-row, 6-column matrix. Okay. Again, these are only for square matrices anyway. Then what you do is you perform row reductions on A until the left-hand side becomes the identity. And the cool part is that the resulting matrix will have the form IA inverse. So as you do all of the row reducing steps on A, this thing over here will slowly turn into the identity. And that's pretty cool. Now, this is definitely a calculator thing, so we're going to use the calculator to do it. So what this turns into is, let's do it once here. I have 1, 2, 3, and 1, 3, 5, and 2, 2, 1. And then we'll put the appropriately sized identity over here. I wrote the wrong thing. 0, 0, 1, there we go. So we're just going to immediately use some calculator help. So here we go. Matrix, and I want let's edit, let's do matrix A. I want a 3 by 6. So I have 1, enter, 2, enter, 3, enter, 1, enter, enter. Good. Second row, I have 1, 3, 5, 0, 1, 0, 2, 2, 1, 0, 0, 1. I just saw this. There's supposed to be a 1 over here. Okay, now let's see if we can, let's take a look at that matrix I just typed in to make sure it's the right thing. 1, 2, 3, 1, 0, 0, 1, 3, 5, 0, 1, 0, 2, 2, 1, 0, 0, 1. Okay, and we all know how to do this now. So matrix, we are going to math RREF, and we're going to RREF the matrix A. And there's what we get. So let's write that down. When you're taking tests, just write this down. This is fine. 1, 0, 0, 0, 1, 0. Oops, not the right thing. Line, okay, 7, negative 4, negative 1, negative 9, negative 9, 5, 2, 4, negative 2, negative 1. Therefore, A inverse is this matrix right here. 7, negative 4, negative 1, negative 9, 5, 2, 4, negative 2, negative 1. Now, as I recall, our calculator will actually do a little bit more than that. Well, let me just try this. I can't remember. Let's just do it. Let's make a new matrix E. Whoops, I don't mean that. Let's edit matrix E. Edit E, and I want it to be a 3 by 3. And let's just enter A in there. 1, 2, 3, 1, 3, 5, 2, 2, 1. Okay, so E is this. Let's see if we can use the inverse button, which we might be able to do. So if I just hit that thing and then an inverse button, I don't know, does that work? Oh, it clearly does. Okay, so, well, your calculators are really good at this, and they know what to do. Okay, so, okay. Next, here's an example. Let's show that B is not invertible. All right, so B is the matrix 4, negative 1, 3, negative 1, 2, 7, 7, 0, 13. What you do to show a matrix is not invertible is you simply start by trying to find the inverse and then show how it's not going to work. Okay, so we'll just put this in. And I want to show you what you'll get, right? If you try to invert one that is not invertible. So something will go wrong, and what will that going wrong look like? So let's go back to our matrix panel here, and we'll just we'll edit the matrix A. It's already the right size, so that's a 3 by 6. So it's 4, -1, 3, and -1, 2, 7, and 7, 0, 13. Okay. Let's see if that's the right thing real quick. A. Very good. Now let's row reduce that matrix. I'm doing this kind of fast. Hopefully we've got some experience with this. Okay, now what is the problem? So the problem, I can't point to it, is in this spot. So what we get is we get 1, 0, 0, that's all fine, and then 0, 1, 0, and that's all fine. Then what we got is there was a number here and a number here and 0. So this matrix does not row reduce to the identity, right? And that's a problem. So our algorithm for creating the inverse runs into an issue, okay? And what it really means is that this row down right here is a linear combination of the first two rows, and more on that word later. But you can make this third one out of these first two, okay? So that's the reason why. And so it's kind of like having 3x plus 4y equals something, and 6x plus 8y equals something, okay? So this is just a multiple of this one, all right? And so you can sort of make it out of those. All right, so that is the problem here. So we will not be able to find the inverse. So in any case, you start by trying to find it, and then you'll be able to. Okay. So here we go. The last example of this particular video. No, that won't be. One more example. All right, so here's a matrix A, and I want to first find the inverse. So let's go ahead and do that here. You can sort of tell some things by looking at it, but maybe we'll more on that later. Let's edit the matrix. E to 3 by 3, and it's 1, 1, 0, 2, 1, 0, 1, 4, -1. Okay. And that was the matrix E, I believe. There we go. All right, so what is E inverse? Oh, there it is. Okay, so this inverse is, again, calculators are good for this, right? -1, 1, 0, 2, -1, 0, 7, -3, -1. Good. Now let's solve this system right here. X plus y equals 3, 2x plus y equals 7, and x plus 4y minus z equals -1. All right, well, what does this look like in matrix form? Okay, x, y, z goes there. 3, 7, -1. So those are the solution column there. All right, now it's going to be 1x, 1y, no z, 2x, 1y, no z, 1x, 4y, -1z. What is that? Oh, that's the matrix A. All right, so because this is A, that theorem I had before says that the x, y, z is simply going to be A inverse B. So I'm just going to have to multiply -1, 1, 0, 2, -1, 0, 7, -3, -1 times 3, 7, -1. Is it always the case that you have the inverse sort of just sitting here to do? And the answer is no, but I wanted us to kind of think about how this works. So in the first spot, I have -3 plus 7 is 4. 4. Then 2 times 3 is 6 minus 7 is -1. And then the last one, let's see if I can do this. I might cheat a little bit. 7 times 3 is 21 minus 21. Oh, that's easy. Those are both negative, so that's just 1. Right? 7 times 3 is 21. Negative 3 times 7 is 21. Those both cancel. And then negative 1 times negative 1 is positive 1. Okay, so I just solved the system, right? So x is 4, y is negative 1, and z is positive 1. So this is a very useful tool for solving systems if you have access to the inverse matrix. Good. All right, now the last thing of the video. There's a bunch of things that are related, okay? And this is kind of like if you give a mouse a cookie, if you've ever heard that thing. If A is an n by n matrix, then there are a bunch of things that are equivalent. And I say that we give mouse a cookie. If you remember that book, it starts off, if you give mouse a cookie, then this, and then if you, want some, cookie, then milk, and then towel, and then a bunch of stuff. And then the very end is, and if he gets that, he's going to want a cookie. Okay, so then all of these things, sort of, if any of them ever happen, then you're going to end up doing all of them over again. So the same thing goes here. So if A is invertible, okay, all of these things are equivalent. So if A is invertible, then it is row equivalent to the identity, meaning you can row reduce to the identity, all right? And that sort of makes sense because of what we saw in this example B up here, okay? So if it's going to be invertible, it has to row reduce to the identity, and if not, it's not going to be invertible. Good. And if it's row equivalent to the identity, then it only has the trivial solution. And think about that. That's because you're going to have just the identity here as you row reduce, right? And these are all going to be zeros over there, so only the trivial solution is going to work. And if this is only the trivial solution, then for every n vector b, it's going to be consistent, right? If you change these to not zeros, if you just change those to numbers, it's always going to work because it's going to row reduce the identity, and you're just going to have things over here. And that's going to be a unique solution, all right? And if you're going to be able to get a unique solution, that it means that it was going to be invertible, okay? So these are the things that go together. Now, if we were teaching a linear algebra class proper and doing the full thing, we'll see how far we get with this theorem, but there ends up being like 20 things that are all equivalent to one another. But the thing I really want us to kind of think about is that the invertibility and being row equivalent to the identity. Okay, so those are kind of the main points. And if you get how those work, then everything else kind of follows after that. Okay, now in the next video, I'm going to talk about kind of why this is true. Okay, so why invertibility and row equivalentness are equivalent. Okay, and I'll go through the machinery for why that works.